This is the three-phase programmable voltage source in which 220 kV is used. 220 into root 3, you will get 381 kV. 381 E3, 50 Hz. Frequency is 50 Hz. Load flow, it is swing bus. And this is the resistance. Small resistance is connected to avoid the errors. So that is 1 milli ohm. And this is the three-phase VI measurement. And now this is nominal pi model. Power frequency 50 Hz. This is the positive sequence resistance 0.02. Zero sequence resistance is 3 times the positive sequence resistance, 3 into that. Similarly, inductance and capacitance also positive into 3 times, you will get the zero sequence. And line length I have given 400 kilometers. You can change this line length. This is the three-phase VA measurement to measure the receiving end voltage. This is to measure the sending end voltage. Okay. Dmux is used to get the signals. VABC, three-phase signals separated. Here also three-phase signals separated. RMS is used to measure the RMS value of the sending end voltage as well as the receiving end voltage. So this is the discrete power GUI. Once you simulate this, you will get the result 229 kV sending end voltage, 262 kV receiving end voltage. So this is the power measurement. VABC and IABC are the inputs. P and Q are the outputs. To get the RMS value, this is instantaneous value. To get the RMS value, let us use RMS block, and you can have the display here so that you can measure P and Q. Okay, the P is very low and Q is very high due to low resistance and high inductance of the line. Now you got the Ferrand effect. This is the Ferrand effect of the system. The power system is considered. Now how to mitigate this Ferrand effect? So by using simple reactor, you can mitigate the Ferrand effect. So this, in addition to the previous example, we have used inductance of 4.75. You are not getting exact value with the design values. So from the design values, once again you need to check it out to get the desired results. Now you can simulate this one. You'll get the 229, 229. Small deviation is there in the receiving end. So this is about compensation with reactor. So the small deviation may be controlled with the control reactance, and particularly this reactor is suitable for no load only. If you want to change the load from no load to 1/4 full load or small load, it may give different results. So therefore, in order to provide the effective control over transmission system, you need to go for thyristor control reactor. Thyristor control reactor. So this is the thyristor control reactor. In addition to the, so this is okay with the distributed line. We'll go for Now this is the distributed line. This is the nominal pi model. Same line with the TCR. This is the TCR. This is from ABC. We have three-phase breaker. Breaker is open initially. It is closed at 1 by 50 first cycle and open at 5000 cycles. So therefore, this logic is used to close the TCR whenever it is required. But here, so manual control, you can use this logic. So other parameters you no need to use. You can use default values. This is the breaker. This is the reactor 9.75, which is different than that of the fixed value. And here phase A, phase B, and phase C. Thyristors T1, T2, T3, T4, T5, T6. And the firing of each thyristor, it was adjusted with manually 27 degrees, but so you need to change the firing angle in the closed loop by using closed loop control. So anybody is interested, you can do it as a mini project or project. So after doing closed loop control, you can write a paper to present in conferences or journals. So 27 degrees was obtained. The manual control after some iterations. 27 plus 180. This is the T1 and T2 firing. So it is fired at 27 degrees. Second one, it is fired at 180 plus 27. So this is 27 plus 120. Second phase plus 120. 27 plus 120 plus 180. Second thyristor of the second phase. Third phase 27 plus 240. Second one firing is 27 plus 240 plus 180. And this breaker is initially open. At first cycle it is closed and it is open after 5000 cycles. So you got 229 volts, 229 kV, the sending in voltage, 228.5 kV receiving in. Still you can tune this. So therefore, minute changes, you need to go for closed loop control. Okay, this is the mitigation of errant effect with thyristor controlled reactor, TCR. Okay, this is the open in line or no load line. So this is the TCR, three-phase TCR. You can write it as three-phase TCR. Okay, let us look at the waveforms. These are the waveforms, receiving in voltage and sending in voltage waveforms. Okay, receiving end we have harmonics. Therefore, the sine waveform is not purely sinusoidal, but harmonic content is very low because firing angle is very low value. If you use firing angle of higher value, so you will get the more harmonics. Similarly, you can also measure one is sending in voltage R phase, the other one is receiving in voltage R phase. So it is better to use mux. You can use mux here. This combination is better. Small variation in the primary sending end and receiving end voltages. Okay, it can be accepted which is within the acceptable limit. But of course, if you want to control precisely, go for closed loop control. R plus or minus 5% is accepted. So this is about TCR control and mitigation of current effect using TCR. Okay, so PS students, you can use one of the course project. This is one of the course project. Serial H number కాకుండా remaining people you can do it. Okay, you can also do it with distributed line. With same parameters, you can use distributed line and do it. So let us do it. So you can take distributed line. So I'll remove this one. Now I'm connecting distributed line instead of nominal pi line. Okay, in the nominal pi model, I'm copying the data, same data. It was already taken. So all the values are same values. Now let me simulate this. To 25.7. So for distributed line, the compensation is somewhat different. Again, you need to change the firing angle for getting the exact equal value. So this is about Ferrand effect and its mitigation. Now let us discuss about transmission line from no load to full load. From no load to full load, what will be the variation and how to mitigate by using SVC. So for this, you need to understand what is SVC, FCTCR and TSC TCR. So we'll go for FCTCR and TSC TCR devices. So each device, what we simulated, is an assignment for one of you. So you can follow one sequence for PE students. Roll number 1. First one is Ferrand effect, study of Ferrand effect for transmission line with nominal pi as well as distributed lines. First one. Second one, mitigation of Ferrand effect by using TCR for both nominal pi model and distributed lines. That is the second assignment. Roll number 2, roll number 3. Roll number 3. Okay. Now let us discuss about FCTCR type SVC. FCTCR type SVC. So this is the FCTCR type SVC in which the compensation can be provided negative to positive, that is leading to lagging, with the help of FCTCR type SVC. Here in FCTCR type SVC, if you go for the design, then you need to study the reactive power variation from no load to full load. From no load, you can obtain the TCR rating. From full load, you can obtain the fixed capacitor rating. So that all together, you need to compensate transmission line at no load and also at full load. So for that, you need to provide the TCR with high rating as that of the capacitor rating, and you can control with the delta with the firing angle alpha, so that you can provide the continuous control of reactive power up to some extent. So, but it has some disadvantages. The TCR size will be bulky. Okay, TCR size will be bulky, and it injects more harmonics into the system because of the bulky nature. It injects more harmonics. So therefore, you go for TSC TCR type SVC. So that we'll discuss again. So now this is a single phase FC TCR type SVC. So this is the this is the assignment for roll number 4 in PE. Assignment for roll number 4. Now let us understand. So this is the AC source, 230 volts, 50 hertz, voltage, and apply. This is the resistance 1 milli ohm. This is C. This is C. So this is 7 millifarads. And this is the current measurement block, which is connected in series with the total current, line current. And the THD block is connected to measure the THD content of total current. And this is the fixed capacitor. That FC. And this is the TCR. In the TCR, we'll connect the current measurement unit, and across the unit you can connect the voltage measurement. Mux is given, to which one signal is from current and one signal is from voltage, and the output of the mux is given to scope. And to measure the THD content of the current, THD block is used and display. And this is the TCR. In series with the TCR, you have connected the ammeter or current measurement. And the TCR is combination of inductance and anti-parallel combination of thyristors. These two are the thyristors. Anode and cathode are connected on both the sides, and gate is given. Gate is given to the pulse generator 1 and 2. This thyristor 1 and thyristor 2, pulse 1 and pulse 2 respectively. And this combination is connected in series with the inductance 3 millihenries. And this firing is, so this is the amplitude 10, time period 1 by 50, 0.02, and the pulse width 50, delay angle 120 is given. Now for the thyristor 2, it is 120 plus 180. The firing angle is 120 plus 180. Now we can simulate it, and you will get the 48.7% THD in the TCR. Total THD is 20.42, and these are the waveforms. TCR waveform, it may not change with the TCR with 120 degrees firing angle. You will get the same result in the TCR current. You can note down that you can note down this roughly. Yellow color is voltage waveform, red color is current waveform of TCR. And coming to fixed capacitor current, this is the waveform of IC capacitor current. It is nearly sinusoidal with some spike. Due to switching action, you'll get the spikes. You have some transients are there, so you may not get pure sine waveform. So this is the IC, and this is total current I through the line. This is the FC single phase FC TCR type SVC. So roll number 4, you can do this simulation and submit me the assignment on PE, power electronics. And the THD content 48.7% the TCR and 20.4% the total current. You can note down that. Okay. Now coming to TCR. Now this is the 3-phase TCR. So this is simulation of three-phase TCR in the roll number 5. Roll number 5 assignment of power electronics. So look at the figure. This is the three-phase source, 50 Hz, and short circuit capacity 1000 MVA, and phase voltage 230 volts. And here in the phase A, ammeter is connected to measure the total THD of each phase. It is a balanced source, so all three phases are symmetrical, except the phase difference between any two phases is equal to 120 degrees. This is the subcircuit. This is the TCR subcircuit, which contains the thyristor 1 and 2 antiparallel combination connected in series with the inductor. So this inductor maybe you can use the RLC load also, in which inductive reactive power 1 into e power 5, voltage 230 volts. And the resistance as usual 1 milli ohm. This is the subcircuit of resistance, including the voltage and current measurements. In each phase it is like that: inductance subcircuit, resistance subcircuit, resistance subcircuit. Okay, T1, T2, T3, T4, T5, T6 firing units. So T1 is, so let us 120 degrees, 120 plus 180 in the first leg. In the second phase it is 120 plus 120, 120 plus 120 plus 180. Anti-parallel thyristor. And phase C, 120 plus 240, firing angle is 120 and 240 is the phase displacement between both the phases. This is 120 plus 240 plus 180. This is the firing pattern. Now we can simulate this. .45 THD content. Waveforms: R phase, red color is voltage, and blue color is current. And phase Z or phase R. Okay, you can note down this one. Okay, phase, second phase, Y phase, yellow is the voltage, red is current. Phase, second phase also, the pattern of the voltage and current waveforms are same. Coming to the third phase. Some problem in third phase. Once again, we'll get simulation. It's 240. Change 240 instead of 120. Let us change it to 240. And get simulation. We got the same value. With a different magnitude, some magnitude was changed. Okay, anyhow, you can note down this one, phase C. So this is about three-phase TCR. Now the FC TCR type SVC, three-phase SVC, three-phase TCR and the three-phase FC TCR type SVC, both will be under one assignment. Roll number 4. Roll number 4. So in the FCTCR type SPC, you have connected the ammeter in the line as well as in TCR. So this is the line ammeter which is connected in series with the line. So THD block is also connected to measure the total THD content. And capacitance value 0.9 e power 5, capacitor load, remaining all are same. Now let us simulate this one. 48.92, 33.21. This is the THD percentage of TCR as well as I. This is the voltage and current of phase A or R phase. You can note down this. And total current is the total current of the phase A is like this. You can note down this. IC plus ITCR. Three-phase FC TCR type SVC. Now let us note on the phase B, same pattern, voltage and current, and total current same except initial transient. Y phase RYB. And coming to third phase, let us look at the figure. So this is the phase B, RYB. Blue color is voltage and red color is current. Or rose color. And this is the total current. Initial transient is different, RYB blue color. Okay, roughly you can note down. Okay, if you have the simulation, MATLAB simulation at your systems, in your systems, you can also simulate and get the results. If you don't have systems, you can get the help of your friends and do the simulation and submit the assignments. After completion of your assignment, you can submit second assignment. Okay, in the next class, we'll discuss about other devices